In this video, we're going to look at the deflection of a beam like they would use in construction. So there's a lot of things that are required of this beam. One, that it be the same thickness throughout. Maybe that's the shape of it. That it's made of one single material so that we can apply some physical constants that we know would be available to it. What we're going to be doing is we're going to look at this thing supported different ways. And here's a few of the ways that they'll be supported. One, you might have it in one side embedded in a wall, and perhaps the other side is embedded as well. That's a possibility. So this is embedded. At the ends. We could have something that is simply supported. So we might have little blocks or something like that, and the beam is resting on top. So this might be simply supported. And we could have a situation where one end is just free. So something like this, where perhaps it's embedded at one end, but the other end is free. Something along this line. So with each of these, we're going to study if weight is applied in some way to the beam and see how much it bends. So that's the goal of this section. Remember, there's a lot of things assumed about this, and I'll try to recall them as we go. Throughout, what we're going to be doing is I am going to allow the beam in all cases to start at x equals 0, and in all cases the beam will end when we get to x equals L. So its length will be capital L. The center, axis of symmetry, if you will go right through the center of the beam. The beam will, of course, be symmetric. So it'll be round, like I'm kind of showing here. It may be square if you cut it. You may see a square or rectangular shape, whatever the case may be. The beam is symmetric about this center, or this axis of symmetry, if you will, which also happens to be the x-axis. We'll use our regular terminology. Y will be the y-axis and x will be the x-axis. And when a load is applied, when we do have some weight on it, we'll see something like this. So we may see that the beam bends in some way, shape, or form. Now, any bending that I'm showing here is exaggerative so that it can show it. Now, it will also still end at L. It won't pull away from it because we're going to assume that the material used in the beam has some sort of flexibility, so it may actually stretch as it bends. So let's take a look at the three kinds of pictures we could get. Now, when I come back to this for a second, I should have mentioned we could have any combinations of these things. Like I could have it embedded at one end, but maybe freely supported at another end. Maybe freely supported at this end, embedded at that end. But there's nothing more than these three possible cases. So let's take a look at what can happen when a load is applied. And remember, my pictures are gross exaggerations of what actually happens. So in a situation where we're embedded, we might have something like this. It'll be straight because it has so much reinforcement near the wall. And then it might dip in the middle, but then come up and flatten out again at the other brace. So this would be a weight somewhere in here. So that's one kind of thing. You can see the shape of this thing looks like that. On the freely supported stuff, it'll come down and make a nice U shape probably. Like so. And then finally, if one end is free, and the only way you can have one end being free is the other one has to be bolted into the wall, maybe something like this. And of course, this flexibility is on purpose so that things don't just shatter when they're subjected to weights. They need things to stretch so that like a building won't just topple over or something like that. For every single one of these, we are going to put it on some sort of a graph where the x-axis does act as the axis of symmetry, but the line that runs through the center will actually be the graph that we have. And the amount of deflection is measured from the x-axis to the middle, or the axis of symmetry of the what you might call the bent axis of symmetry of this, maybe an iron bar or whatever it may be. So this right here will be represented by y of x, except y of x will be considered positive in the downward direction, just like the previous examples. So when this dips below like that, y of x will be considered greater than 0. Okay, so then as we're working here, we're going to let w of x be the weight per unit length. This will be the load that is applied. So it could be centered mostly about the center, like this looks like it. It could be near the end more. Whatever it is, the x will allow us to vary it, if need be, throughout the length of the beam. We have m of x is called the bending moment, and it has two equations that govern it. One of them is that m double prime equals w, so w is related to the acceleration of m, and we also have that m equals e I k. I'm drawing the k to make it look strange because this k is referred to as the curvature. E and I are physical constants. By that I mean E is a measure of the elasticity of the beam, known as Young's modulus. I stands for moment of inertia. Together, EI is a measure of the structural rigidity. K, as I mentioned, is curvature. This K is actually studied in Calculus 3. You have K equals y double prime all over 1 plus y prime squared to the 3/2. Now throughout, we're going to assume the deflection is small. Compared to the length of the beam. In fact, we are going to assume that y prime is very small. So we assume y prime is small, which means that y prime squared is tiny, if that makes sense. If y is, say, 1/10, for example, say the slope is 1/10, then this right here will be 1/100th. Well, you get the idea. In fact, we'll use y prime squared as basically equal to 0. So what happens then is your curvature, which equals y double prime all over 1 plus y prime squared to the 3/2, will be approximately equal to y double prime all over 1 plus 0 to the 3/2, and that equals y double prime. So back up to the equation that I have, m equals EIK. I'm going to replace k with y double prime. So m equals EI y double prime. Now, continuing, go back a little bit farther to what I had earlier. I had m double prime was equal to w. So m double prime equals w. Now EI are just constants. So this means that if I take the second derivative here, I will have EI, the fourth derivative of y, will equal w. And then this is really easy to solve. If we look at the auxiliary equation for the homogeneous equation that we're going to be solving, first, before I even mention that, let me divide by EI. Of course, this is not equal to 0. And now to solve an equation like this, the first thing we do is look at the auxiliary equation. You have m to the fourth equals 0, which means that m has 0 as a 0 4 times. So that immediately means that y sub c will look like c1 plus c2x plus c3x squared plus c4x to the third, not to the fourth. And then our solution will simply be like this. Y equals y sub p plus c1 plus c2x plus c3x squared plus c4x to the third. So figuring out y sub p is actually not that hard to do. And let's start with an example to explain how it works. So for my first example, suppose a beam is simply supported at both ends. So what does that mean? Well, we've already shown it, but I'll do it again. I have some sort of bend. Like, remember, whatever bending I'm showing here is exaggerated. What we have then, if we look at something like this initial positioning here is at 0, 0, so y of 0 equals 0. And over here, remember, this starts at 0, x equals 0, and ends at x equals L. At the end, we have y of L equals 0. Now, other than that, if you look, this is pretty flat near the end here. So whenever you have flatness like this, that means the slope here is fairly constant. But better than that, we have that y double prime of 0 is 0, and y double prime of L equals 0. Because of this flatness here, the second derivative will be 0. I will need this. If you look at this here, the solution will require solving for 4 constants. And that means you're going to have 4 initial conditions. These are typically not referred to exactly as initial conditions, although they're the same idea. These are referred to as boundary conditions because, well, they're at the bounds, at the ends of the discussion. So these are referred to as boundary conditions. So we'll keep all four of those around, and that'll help us solve for all of these. Now, coming back, let me come up with a weighting function. Suppose w of x simply equals w naught. So perhaps we have a constant weight applied throughout the length of the beam. It could be paint even, as simple as that. Maybe years and years of more and more paint will make it droop and farther and farther. Whatever the case may be, this weight is constant throughout the length of the beam. So what does that tell us then? Well, in this solution, I know that I'm going to have all these c's, but the hard part, the only part that takes work, is the y sub p. So we had y, the fourth derivative of y, was equal to w over e I. That means that if I plug in y sub p, it should solve that equation. I'm going to replace w with w of x. Well, I should have done that. W was equal to w naught. And then this is a constant throughout the problem, so I'm just going to integrate 4 times. So y sub p triple prime will be the integral of this thing, and I'll get w naught over e I times x. Now remember, we're finding a particular solution, so I don't worry about constants or anything like that. I just want any y that will solve this equation. Take another derivative. Y sub p double prime will equal w naught over 2ei x squared. Take another integral. Wp prime will equal w naught over 6ei x cubed. And finally, one last integral will give us y sub p, w naught over 24ei times x to the 4th. So my solution will be y equals w naught over 24ei x to the 4th plus c1 plus c2x plus c3x squared plus c4x cubed. Now this is where we look at the boundary conditions. Let me scroll back up for a second. The easiest ones to work with are these things. Let me start with y of 0 equals 0 and see what we get out of that. Y of 0 equals 0. So if I plug that into this, all the x terms will disappear, and this is gone, and all of these are gone. So with that out of the way, my new equation, or my new formula for y, is w naught over 24ei x to the 4th plus c2x plus c3x squared plus c4x cubed. The way you attack these is probably best to stick with the conditions that happen on the left side first to figure out c's, and then you'll have, once you start plugging in L, it gets a little messy. So we had y double prime of 0 was equal to 0. Let me take the second derivative there. So this is really, when we went back here, if I want my yp double prime, it's sitting right up here. It's not really hard to integrate this, differentiate this anyways, because you'll just work, this is just a polynomial really. So I'll get w naught over 2ei x squared plus, when you differentiate twice, the c2x disappears. But here, you'll get a 2c3 plus, and then when you differentiate twice here, you'll get a 6c4x. So let me replace x with 0. That means this part wipes out, this part wipes out, and we'll get c3 will equal 0. So here's what we have so far. Y equals W naught over 24 EI x to the fourth plus no C1 anymore, but we got a C2x plus C4x cubed. Now let's go use the L conditions. We have y of L equals 0. So let me replace x with L, and I get 0 equals W naught over 24 EI L to the fourth plus C2L plus C4L cubed. I'm going to divide out by L. So I will get one equation involving C2 and C4. That will be C2 plus C4 L squared will equal negative W naught over 24 EI L cubed. Now we also had that y double prime of L was equal to 0. Let me grab the y double prime equation again. And so I'll replace x with L. I get 0 equals W naught over 2EI L squared plus 2C3 plus 6C4L equals 0. And I'll take that over on the other side. So negative W naught over 2EI L squared equals 2C3. All right, recall though, 2C3 was C3 was equal to 0. So I can take that out of there. Let me solve for C4 here. I will subtract. Okay, I will divide by 6L. So now I got C4. I can go back up, find out what my equation was involving C2, and now solve for that as well. Here it is. I will grab it and copy. So let me replace C4 with this expression. And this will now become L times L squared, which would be L cubed, equals negative W naught over 24 EI L cubed. Well, that's nice. They have exactly the same things. All of the letters are all the same, so I'll add that to both sides. This is like 2 over 24. So C2 will be W naught over 24 EI L cubed. So let me go ahead and box my C's in. C1 and C3 were equal to 0. So my solution finally is y equals W naught over 24 EI x to the fourth plus W naught over 24 EI L cubed, and C2 was connected to x. And finally, minus C4, where did you go at? Minus W naught over 12 EI L, and that was attached to x cubed. Nearly every book that I know of will simplify this to some extent because there's so much writing here. For example, I will factor out a W naught over 24 EI, and that'll leave me with x to the fourth plus L cubed x. Now, when I take a 24 out of here, that will leave me with 2 minus 2Lx cubed. My next example. In example 1, let W naught equal 24 EI and L equals 1. Graph the resulting function. So let's go ahead and throw those in there. W naught is 24 EI. Well, that's pretty clear. When you plug it in here, that'll wipe those all out. And all this stuff is constant anyways. What really happens is governed by this, where it bends and how far it bends and stuff like that is really more governed by this stuff. If L is 1, then L cubed is 1, and this L is 1. So what we'll have now to graph is y equals x to the 4th plus x minus 2x cubed. I am just going to use your calculator, standard calculator for this. Let me change my y. Let's clear that out. Put in this stuff. X to the 4th. You got to remember to bring yourself back down from there. Plus x minus 2x cubed. Now, remember, the length is 1, so I really don't need to go past 1. What I'm going to do is set my window up, and I'm going to go from 0 to just 1 for the x's. The y values I'll leave from -1 to 1. We'll see what happens. Let me take a look at the graph. So there, you can see it. So look, it looks exactly like what I was saying it did. Let me capture this thing. One of the questions we might want to know, and you can see it's the shape that I have, although it's upside down because we're considering downward y's to be positive. So the actual bending of the beam is a mirror image below here. Anyways, what exactly is the highest or the most deflection from neutral? And that means we need to find this maximum. Your calculator is perfectly capable of doing that. Go to second. What you're looking for is this calc menu. I think I hit trace. Second calc, and you'll be looking for maximum, number 4. Either that or just click the number 4. What it will do is it wants you to pick a spot to the left, clearly to the left of the highest point, and then a spot clearly to the right of the highest point. And then it wants you to pick a guess in between. It's even got the little bounders there. So I hit enter, and it will tell me what I have. And this shouldn't surprise anyone at all that the most deflection occurs right in the middle. So we have 0.5 and 0.3125. So whatever it is, if L was given in meters, then right in the middle of the beam, we have 0.3125 meters is how far that is from flat. This may just be me and not completely understanding the process here, but this number seems awful big compared to the deflections we're talking about. I think the deflections, in order for our equations to really, really be true, I think this number needs to be a lot smaller, but I could be wrong. This time, suppose a beam is embedded at the left end but simply supported at the right end. So the situation we have here looks like the following. We're embedded over here. Let me give myself some space. So it's going to come straight out for a little bit, and then it's going to have its bend, like so. But this end over here is simply supported. So let's take a look at what are possible things we have. Since we have flatness over here, well, first of all, let's get the zero conditions. Y of 0 equals 0. Y of L equals 0. And we also covered last time, since the end of this is flat, its second derivative is 0. So Y prime prime of L equals 0 as well. If you look, this flatness here, though, means that its derivative is also 0 here. So we have Y prime of 0 equals 0. So we use those to figure out our constants. Suppose that W of x equals W naught sine of pi over Lx. So we have a variable force being applied to this structure. That means y sub p, the fourth derivative of it, was W over EI. So that'll be W naught over EI sine of pi over Lx. And then I'll simply integrate my way through to get y sub p. So y sub p triple prime will equal, well, the antiderivative of sine is cosine, negative cosine actually, so we'll have negative W naught over EI. And then when you do this, remember, if you let u be pi over Lx, then the du will be pi over L. When you integrate, you'll end up getting an L over pi cosine pi over Lx. I'll integrate again, y double prime sub p. And each time I'm just going to pick up an L over pi in my integration. So I'll get negative W naught L squared all over EI pi squared times sine pi over Lx. Integrate again, y sub p prime will equal, now the antiderivative of sine is negative cosine, so that will fix this negative to a positive, so we'll have W naught L cubed all over EI pi cubed cosine of pi over Lx. And finally, we're ready for y sub p itself. And that will just become a sine. We'll have W naught L to the fourth all over EI pi to the fourth sine of pi over Lx. And so this gives us the solution y equals, the y sub p part is right in front of us there, y W sub 0 L to the fourth over EI pi to the fourth sine of pi over Lx plus C1 plus C2x plus C3x squared plus C4x cubed. And now we're ready to use our conditions, our boundary conditions. The first one was the best one and simplest one, was y of 0 equals 0. That boundary condition. When you plug, sine of 0 is 0, so that's going to wipe everything with an x attached out and sine of x as well. The only thing that will be left standing when we replace x with 0 is C1. We'll get 0 equals C1. And so my function is a little bit shorter. Y equals W naught L to the fourth all over EI pi to the fourth sine of pi, L over pi, not pi over L, but L over pi, L over pi of x plus C2x plus C3x squared plus C4x cubed. Another boundary condition that we had was y prime of 0 equals 0. So let me take the derivative of this and replace x with 0. Y prime will equal, well, you can just follow up the chain that we had before. This part of it, there's my y prime right there. W naught L cubed EI over EI pi cubed. So this would be cosine L over pi of x plus C2 plus 2C3 of x plus 3C4 of x squared. Let me replace x with 0. Cosine, of course, does not go away here, but it does become 1. And I'll get W naught L cubed over EI pi cubed plus C2. And of course these things disappear and we're able to get C2 rather easily then. C2 will equal negative W naught L cubed over EI pi cubed. I'll circle that so I have reference to it later. I should circle that as well so I don't forget it. So my new function then is y equals W naught L to the fourth over EI pi to the fourth sine of pi over Lx. Suddenly I need to be careful here. Right there, and right there. And we already know that C1 is 0, C2x. So let me go ahead and put that in there. Minus W naught L cubed over EI pi cubed x. Plus we have not discovered C3 yet. C3x squared plus C4x cubed. Now the other boundary conditions happened at x equal to L. So for example, we had y of L was equal to 0. Let's throw in L. When you do that, sine of pi is 0, so this part will 0 out. This part will not 0 out, so we'll get negative W naught L cubed over EI pi cubed times L plus C3L squared plus C4L cubed. Now what I can do is I'm going to add this to the other side. I'll have an out of the fourth there. So we have W naught L to the fourth over EI pi cubed equals C3L squared plus C4L cubed. I'm going to divide both sides by L squared, and I get W naught L squared all over EI pi cubed will equal C3 plus C4L. So I'll use that. Another thing we had, another boundary condition, was y double prime of L was equal to 0. Let me have my y double prime back. And then C3 was attached to x squared, so we're going to get 2C3. C4 was attached to x cubed, so we're going to get 6C4x. And then I'll replace x with L once again. When you do that, if I plug L into here, sine of pi is 0, and it looks like we'll have 2C3 plus 6C4L. I'm going to divide that by 2. C3 plus 3C4L. So I have a pair of equations and two unknowns. L is considered known. So let me grab this one here with this one here and solve that system. So I have C3 plus C4 times L equals W naught L squared over EI pi cubed. And on the other hand, we have C3 plus 3C4L equals 0. Now, you can solve this simply by subtracting. You'll be able to get L or C4 quite easily. But I think just to remind us of Cramer's rule, I'm going to go about getting C3 and C4 using Cramer's rule. So if you remember, if I want C3, I need to replace that column with the result column. So W naught L squared over EI pi cubed. I'm going to need a bigger one of these. And then here I'm going to have L and 3L. And we're going to divide by the coefficient matrix, which will be 1, L, 1, 3L. So when I multiply through, I'll get the 3L times that stuff. So that'll give me 3W naught L cubed, 3W naught L cubed over EI pi cubed. Divided by the stuff underneath. So I'm going to put a big division sign here. This way is 3L minus 1L will be 2L. So it looks like we have 3. This L will take away from that. So I have 3W naught L squared all over 2EI pi cubed. And I'll play the same game for CL. I already have this stuff here, which down here. So my C4, okay, now I'll have for my first column 1 and 1. But over here, I need to replace it with the result. So W naught L squared over EI pi cubed, and then a 0 here. And then from this part, I've already figured out that down here is 2L. So when I multiply, that'll be 0, but then I'll have negative W naught L squared all over EI pi cubed divided by 2L, which will give me negative W naught, I'll take out an L, so L over 2EI pi cubed. And I have my solution now. So my Y equals, let's go ahead and get everything back that I need. As before, we'll factor a bunch of stuff out front to make it seem like less complicated than it actually is. So let's factor out a W naught. Let's factor out, how much L do I have? The most I have is just 1 L. I have an EI attached to everything. Actually, you know what? If I factor out a 2 down below, that'll just make 2's up here. So let me go ahead and do that. There's a pi cubed attached to everything. And what are we going to be left with when I take all that stuff out? I'll be left with an L cubed over pi times sine of pi over Lx. Then I'm going to have negative 2 L squared x, and then I'm going to have plus 3 Lx squared, and then minus x cubed. And I need one more 2 here, and I'm good. I think let's check it out, make sure everything's good, and that will be our y. For the last example, let's just take a look at what kind of deflection happens with this particular problem. So let's let W naught equal 2 pi cubed EI and L equal 1. That way our equation then pretty much nullifies all the stuff out front. So basically when L is 1, that's not going to be a big deal. W naught was made to wipe out that stuff. So we will have 2 over pi sine of pi x minus 2x plus 3x squared minus x cubed. And I won't bother with all of the details. You can graph this on your calculator. But it does look like the mirror image of the picture that I drew. You'll have the slump will happen farther out than before, and this maximum point, the maximum deflection will be at 0.573, and its deflection will be 0.271. So notice that it does look like a mirror image of the picture that I drew at the beginning of this problem.